Example 1.4.2b. Calculate the amount of fuel used to generate 1 kilowatt hour of electricity from coal, natural gas, and petroleum, assuming the following power plant heat rates and fuel contents. And then we're given this table that tells us what the heat rate is for the three different plant types. We can see that coal has a heat rate of 10,089 BTU per kilowatt hour, so the lowest efficiency of the plants. Natural gas has a heat rate of 10,354 BTU per kilowatt hour. That would be the highest efficiency of the three types. And then petroleum is 10,334 BTU per kilowatt hour, so kind of in the middle there. Obviously, each of those plant types will require a different fuel input source. Coal-fired plants use coal, nat gas plants use natural gas, and petroleum plants burn petroleum or fuel oils. And so we need to know what the energy content of those fuels are. And the table tells us that the coal that this plant is using has 19,210,000 BTUs per short ton. So a short ton is a weight measurement equivalent to 2,000 pounds. And there's a little note there that just reminds you that that's an average value for coal. Not all coal is created equal, so that's a 19.2 million is an average value. And then we got similar numbers for natural gas and petroleum. So those are our givens, right? The info in table 1, the heat rates are important and the fuel contents are important. So those are what we'll be using to calculate the amount of fuel. And so what we're being asked to solve for, of course, the amount of fuel necessary for each of these plants to produce 1 kilowatt hour of electricity. So it's a relative figure of merit. So the solution to that is going to be based on the heat rate and the fuel content. We're simply just going to divide the heat rate by the fuel content, and that tells us how much fuel is necessary to produce 1 kWh. Whoops, sorry about that. So back to the problem. For the coal plant, we're going to divide 10,089 BTU per kilowatt hour. And we're going to divide that number by the fuel heat content of coal, which was 19,210,000 BTU per short ton. So I'm writing both of those as fractions. And what you can see here is, due to dimensional analysis, the BTU in the numerator and the denominator will cancel out, and that will leave us with a units of short tons per kilowatt hour, which is what we're interested in. How many short tons does it take to produce 1 kilowatt hour? So rewriting that, we got 10,089 divided by 19,210,000 short tons per kWh, and if you carry that math out, you get the answer of 0.00052 short tons. So like 5/10,000 short tons per kilowatt hour. So then we just want to repeat the process for natural gas and for petroleum. So nat gas had a different heat rate. It was 10,354 BTUs per kWh, and we need to divide that by the energy content of the natural gas we're using, which was 1,025,000 BTU per MCF. And so that gives us 0.0101 MCF per kWh. And then for petroleum, we take the heat rate of 10,334, divide that by the fuel content, the fuel heat content of 5,892,000 BTU per barrel, and that's going to give us a final answer of 0.00175 barrels per kilowatt hour.